Assalamu alaikum everyone. I am Sabahuddin Ahmed, and on behalf of NUST Physics and Astronomy Society, I would like to welcome you all to another amazing session that we have planned for you. Today we have with us Dr. Mansoor Rehman, an Associate Professor of Physics from Quaid-e-Azam University. Dr. Mansoor completed his PhD from University of Delaware, USA in 2011, and then his postdoc from Switzerland. His research interests include inflationary cosmology, primordial gravitational waves and black holes, cosmic strings, and dark matter. Today, Dr. Mansoor is here to deliver a talk on finding the missing baryonic matter using the FRB flashlight. Just before we start this event, I would just want to remind our audience that you can post your questions throughout the session and Dr. Mansoor will definitely answer them at the end of his talk. With that, I would just unshare my screen. Sir, you can share your screen now.
Okay. Thank you, Sabahuddin, for the introduction and for the invitation. So, yeah, let me see. So, can you see my slides?
Yes, sir.
Okay. So, the topic of my talk is finding the universe missing matter with the fast radio burst flashlight. So, and actually my research area is related to the physics of very small and the physics of very large. The physics of very small is particle physics, and the physics of very large is cosmology. So I work on the area where these two physics combines. So from that point of view, from a particle physics perspective, I say things at a very fundamental level. So this is the present picture of fundamental physics. So in we describe, as you know, that there are four forces: strong, electromagnetic, weak, and gravity. And we describe these strong electromagnetic and weak forces by the standard model of particle physics. Actually, in standard model of particle physics, these electromagnetic and weak forces are unified, and we may call this force electroweak force. So at this level, we have these two forces, but at low energy, this electroweak force breaks or splits into two forces. One is electromagnetic force, which is described by the quantum electrodynamics, or its classical version is classical electrodynamics, and there is this weak force. And the gravity is not described in this standard model of particle physics. It is described by the Einstein general theory of relativity. So just to give you an idea of the strength of these forces, you can see that the strong force is the strongest of all, and gravity is the weakest of all. And this electromagnetic and weak forces lies in these two extremes. So this is the picture. And what about the fundamental particles? In particle physics, this standard model of high energy physics, you have basically four types of elementary particles. One is quark, second is leptons, then gauge bosons, and then a Higgs boson. So quarks carry color quantum number, and they participate into the strong interaction, whereas these leptons don't carry the color quantum number, which is necessary to participate in the strong force. And these gauge bosons mediate various type of forces with strong electromagnetic and weak forces. and the Higgs boson is responsible for giving masses to almost all of these fundamental particles. So from these fundamental constituent, you can make some bound states. So here are some bound states from quarks. From 3 quarks, you can make baryons. So up and down quark, I mean, you can make proton. From up down you can make neutron. So this is the RD matter stuff, and from quark anti-quark you can make mesons. So in baryons, these protons and neutrons are the most stable particles, and for mesons, I mean, all the mesons are unstable particles, and in lepton sector, electrons are the most stable particles. So I mean, if you consider the matter from these particles from a particle physics point of view, so this constitutes the 5% of the total energy budget or total matter budget of the universe we know about. So this constitutes only the 5%. So I will be talking about the rest of 95%, but my talk will be mostly related to this 5%. So just a warning, I mean, the astronomer use a different type of language when they say baryonic matter. When they say baryonic matter, it it means that it is the stuff made of protons, neutrons, and electrons. So in astronomy, the term baryonic matter is used more loosely, since on astronomical scale, protons and neutrons are always accompanied by the electrons. So they form a neutral atoms and things like that. So astronomers therefore use the term baryonic to refer to all objects made of normal atomic matter, essentially ignoring the presence of electron, which after all represent only 0.005 of the mass. So basically it's just proton and neutrons when you talk about the mass. So what's next? So let's talk about general theory of relativity briefly. So Einstein says that the gravity is a kind of pseudo force, is actually curvature of space. So matter, the presence of matter makes the space curve, and then space tells the matter how to rock and roll. So this is a famous quote by John Wheeler. So according to Newton, the gravitational law you can write down in this form in Poisson equation. So this is your gravitational potential, and this is the mass density. So this is a type of scalar, I mean, theory. You have this scalar potential and this scalar. Einstein made this equation relativistically covariant. I mean, he added the relativity into it, so that, I mean, you can see, and his equations, the Einstein equation, which describe the general theory of relativity, are actually tensor equations. So he described the gravitational force as a tensor theory of gravity. So this mass density is replaced by the energy momentum tensor. You know that the energy, the zero component of energy momentum tensor is mass density, and this scalar potential is actually related to the metric tensor. The metric tensor describes the geometry of the space. So here he got, I mean, here is the covariant form of this Einstein general theory of relativity. So there is also lambda parameter, lambda constant, which is called the cosmological constant, and we will describe its relevance later on. So let's go forward. So just to give you some idea about the cosmology and astronomy. So what is cosmology? Cosmology is the study of universe as a whole, including its origin, its nature, its evolution, its eventual fate. Whereas astronomy is the study of celestial objects and related phenomena. Objects of interest include planets, moons, stars, nebulae, galaxies, and comets, etc. So in astronomers usually use these astronomical units, which is a typical distance between among the planets in the solar system. Astronomical units, which is of the order of 10 to the 11 meter, whereas cosmologists use let's say light year units or megaparsec units. So 1 light year is actually a distance which light travels in 1 year, and it is equal to 6.33 into 10 to the 4 astronomical unit, or in meter it is around 10 to the 16 meter. So current radius of observable universe is around 46.4 billion light years. So, and age of the universe is around 13.8 billion years. So just to give you idea of the scales between cosmology and astronomy. So we have described standard model of high energy physics briefly, and we also saw the general theory of relativity. So if you combine these two with a cosmological principle, which says that your universe is isotropic. Isotropic means same in all direction, and homogeneous. And homogeneous means it is same at every point. So combining these, this is the assumption which is called cosmological principle, and it holds at sufficiently large scale, not at a small scale. So sufficiently large scale, our universe is isotropic and homogeneous. So using this cosmological principle and the standard model of particle plus general relativity, you can define a cosmology of Big Bang cosmology. So this depends on the Big Bang theory. So, this is just American television sitcom, which was on air, I think, in September 2007, and it, they played, I think, 279 episode of this sitcom, and I saw a few episodes when I was doing my PhD. So you can also see this very interesting television sitcom. So what's the consequence of this hot Big Bang cosmology or theory? So the first one and the most important one is it predicts that universe is expanding, which was experimentally observed by Edwin Hubble. And he actually observed the motion of galaxies moving away from each other. So he plotted the velocity of recession versus distance between the galaxy, and so he saw that these two are it is a linear plot. So, and the proportionality constant is actually the Hubble constant. So the universe is expanding and these galaxies are moving away from each other, and from this you can calculate the Hubble constant. The most recent measurement of this Hubble constant is given by Planck satellite, which is 67.66 kilometer per second megaparsec. And from this Hubble constant you can calculate the age of the universe, observable universe. So T naught is inverse of H naught, which is around 13.8 giga-year. Second prediction of this Big Bang theory is the Big Bang's afterglow. So there is a leftover radiation, which is called cosmic microwave background radiation, which was first measured by Penzias and Wilson in 1967 using their antenna, then by Kobe satellite, and it was refined, and it was further refined by WMAP. This is a NASA project, and this is the WMAP in 2003 it was launched. And then there is another satellite, which is Planck satellite, which was, I think, launched in 2009 or so. So even then, now, so what is cosmic microwave background radiation? So it is actually in the very early universe, the matter and the radiation were coupled. What do I mean by coupled? So when electrons and protons try to form a neutral atom, so these photons just come and break them away. So these photons were energetic enough so that they can ionize these atoms so frequently. So in this way, the photons and this matter field were coupled. So after, the temperature drops, these photons do not have enough energy to ionize this hydrogen atom. So the neutral atoms forms, and this photons or the light decouples from the matter. So this is that incident. Uh, these radiations spreads throughout the universe, and we call it the cosmic microwave background radiation. So if you see its spectrum matches with the black body radiation, from there you can calculate its temperature and its wavelength. It lies in the microwave region. So, so this is the prediction of. Sorry, this comes again. Or what did I do? So you can also, these when these photons are coupled with matter, the universe was like fog. Foggy. You cannot see the universe when these matter and photons are coupled. But as soon as these photons decoupled from the matter, the universe becomes transparent. So this is the last scattering surface where this radiation uh, the radiation decoupled from the matter. So this situation is very similar uh, to the one which is shown here. You said we can see only the surface of the cloud where light was last scattered. You cannot see beyond these clouds, because here this is similar to this situation. So another, this cosmic microwave background radiation, you can even detect it with your TV set. And here, this professor is showing the TV set, and in this noise, about 1% of the static noise on TV screen is from the Big Bang fireball. So why, this is the temperature and isotropy uh, plot, a map of cosmic microwave background radiation. So on average, the temperature of cosmic microwave background radiation is 3 Kelvin, but there are very little or tiny fluctuation, which you can see here in blue and red. And these are of the order of 10 to the minus 5. So there is a 10 to the minus 5 order fluctuation around 3 Kelvin. So these blue dots I think are hotter one, and these red ones are the colder one. And this is the full sky map. You can compare it with the world map. So we know that the world is spheres, but you can map it. You can make a two-dimensional map, this oval map, using latitude, altitude angles. So this is the same map. We get cosmic microwave background radiation from all direction, and then we can transform it to in this oval map. And from there you can see, the direction. If you are at the center of the Earth, and you are looking in the direction of, let's say, which your line of sight is passing through the nest, let's say, then you might be seeing this dot here. Maybe this is the colder one or the hotter one. So this is the map, and here I have shown that these small tiny fluctuation is temperature is actually should be there, and it is coming from small density perturbation in the very early universe. And these density perturbation are necessary for structure formation, for the formation of galaxies and their cluster, supercluster, the structure we see around us today. So enough for CMB. So the current model, you can say the fitting model of this information From these noise, the cosmic wave background radiation, we calculate the power spectrum. From that power spectrum, we extract some information by using minimal 6-parameter fitting, and that 6-parameter fitting model is this lambda CDM model, and we use uh, in these fixed parameter. I will just describe the ones which are relevant for our discussion. So one is this lambda part. I mean, this the dark energy part, which is about 63.3%, and other big part is the dark matter part, which is 26.8%, and the smallest part is actually the ordinary matter part, which is around 4.9 or around 5%, which I was talking about, which we know, I mean, from standard model, which we can call the baryonic matter. So this 5% is the baryonic matter. So we know these things from the CMB, then from after extracting information from the CMB, which is the physics of very early universe. So this dark energy part, I mean, you can fit this dark energy from this lambda constant in the Einstein equations, and but this dark matter, the dominating part of dark matter is actually the cold dark matter. CDM means cold dark matter, which means the candidate for dark matter, the particle which are candidate for dark matter should have tiny velocity. It should not be moving relativistically. So these two parts we will not be talking about. Our concern is this ordinary matter. However, this fitting model describes that once we add all these parts, so we get the density becomes equal to the critical density of the universe, so which is given by this. So from here, I mean, they can extract how much matter should be there. This 5% value you can extract by using this lambda CDM model, and by fitting this lambda CDM model with the CMB data. So this is one way to know that there should be 5% of baryonic matter. Second one comes from nucleosynthesis. Let me go further. So Big Bang nucleosynthesis, using Big Bang nucleosynthesis, this was a paper by Alpher, Bethe, Hans Bethe, and Gamow. So they made this model in 1948. In 1948, 1 year after our country came into existence. So, and after Second World War, I mean, these nuclear reaction rates were available to scientists, and then Gamow studies these nuclear reactions with his PhD student. This Alpher was his PhD student, and when they about to publish this paper, Gamow thought to include, I mean, he included Bethe just to have these three named alpha, beta, gamma, alpha, beta, Gamow. But his PhD student was not happy to include Bethe's name at this last moment due to his some personal reasons. So it was possible to calculate using this Big Bang theory. You can calculate the relative abundances or relative concentrations of light nuclei like helium 4, helium 3, deuterium, or lithium. So the key thing is you only need to know a single parameter, which is actually the baryon to photon ratio, which is around 6 to 10 to the minus 10. With this single parameter, you can calculate the relative abundance of all these light nuclei with respect to hydrogen. The ratio predicted by mass are 0.25 for helium 4, and for deuterium it is 10 to the minus 4 for this. And from these observations, and from this baryon to photon ratio, you can also calculate using this Big Bang nucleosynthesis that there is 5% baryonic matter. So these are two independent measurements, Big Bang nucleosynthesis, and from CMB data, we know there are 5% baryonic matter. So this is just the evolution of different components of this energy budget. I mean, this dark energy stuff is, if it is described by the cosmological constant, it will remain constant. whereas this radiation density scales like 1 over volume. Matter density scales like 1 over volume when you stretch the universe, so it will go like this. And for radiation, apart from volume, you also have a scaling length coming from the wavelength of the photon. So this has a higher, suppression factor a to the minus 4. So different evolution, how does the different components, matter means matter, dark matter plus ordinary matter, and this is the dark energy part. So currently, the dark energy is the dominated part, but in the early universe, it was mainly radiation dominated above, just to give you an idea how the different components were evolving. So current, computer simulation show us how the matter part of the universe is distributed in the universe. So this is called the cosmic web, and it is composed of the interconnecting filaments of clustered galaxies. So there are clusters of galaxies, clusters and supercluster of galaxies, and the gases stretch out across the universe and separated by joint void. So this is the voids, places which are empty. So this is, the computer simulation, so of the matter. So what was the story in 1999? In 1999, this ordinary matter, which we think is about 5% from the CMB and big nucleosynthesis estimate. So they actually detected, the direct detection was possible because most of this matter was in these stars. They are luminous, you can see it through detectors, and so they saw it contains, the star contains 7% of the this ordinary matter, and this cold gas in galaxies and hot gas in galaxies, they contains about 2% and 5%, and there is also some hot gas in galaxy cluster, it was about 4%. So these all add up to about 20% of the matter which was known in 1999. So where is the rest of the baryonic matter? So not all ordinary matter is actually glowing brightly or illuminated by nearby stars. So it is not dark matter, but it is the ordinary matter which is just in darkness. So they thought, these missing baryons could be certainly hiding in certain immense filaments of gas that sit between galaxies, and this medium is generally known as the intergalactic medium. So they are saying that this missing baryon could be hiding in some of these filaments, which they see, and these filaments and these things, this medium is called intergalactic medium. So one way to find this ordinary matter, this missing baryonic matter, you can find it if you use a backlight. But so how can we use a backlight? So quasars are the perfect, source of backlight. So you can see a picture of quasars. These are, the black holes, kind of black holes which emit this light. So these are they are very far away, and they are very bright. So a very far away source, and they are also bright. So it can serve as a backlight for these filaments, which I have shown you in the previous slide. So it means it is connected with some with early universe, and these are coming from cosmological distances. So those are the perfect. Why they are perfect backlight? Because their luminosity is very high. So luminosity, just to give you an idea, one quasar's luminosity is greater than the luminosity of 1000 galaxies, and this is the early universe quasar where the light is coming to us. And how can we detect the missing baryons? So in order to understand the physics, how this detection thing works, so consider the hydrogen atom. You have proton, and then you have electron cloud, let's say it is in the first excited state, and when this make a transition to its ground state, so you get some light in the ultraviolet region whose wavelength is 121.6 nanometer, and this transition is called Lyman alpha transition. So what about this? And this transition, and if this light is coming from these quasars, so you can see, I mean, these are very large distances, so they will these distances, the light coming from these large distances will be highly redshifted. Highly redshifted means its wavelength will shift towards the uh, red part of the spectrum. So it started with this wavelength, which was 121.6 nanometer, something around here, and it got redshifted. When you detect it, it got redshifted, and it has a peak around 560 nanometer. But if you see this spectrum closely, I mean the light coming from these quasars, I mean, so if you see the light coming from uh, uh, this spectrum, you see some dips in this spectrum. So these dips can come from the absorption. These are the absorption spectroscopy. So why it is happening? So these dips are actually, there is a neutral hydrogen in the light line of sight. You are here and quasars are there, and the light coming from here, I mean they got absorbed, I mean, by this hydrogen atom, which are excited from the ground state to its excited state. So one, two, three. So these bumps, just to show you, these three bumps depends on where this bumps comes. This the position of this dip actually tells you the location of that hydrogen atom. So these are not three hydrogen atom, neutral hydrogen. There are many neutral hydrogen atom, and you have lot of these dips and these things. So this is the two-dimensional plot is actually called the Lyman alpha forest, which shows you these spikes, different spikes, this absorption. These are called absorption spectral lines. So from this, I mean, you can calculate actually the neutral atom and the mass of the neutral atom between these quasars and you. So now adding all neutral hydrogen makes up to almost 50% of the baryonic matter. So after this addition, we get, we know almost the 50% of our baryonic matter. So where is the other 50% of baryonic matter? Let me show you first. So this much we know, this much. So this part is actually the cool intergalactic gas. So from that intergalactic medium, we have detected the cooler part using this alpha forest thing. Now almost 50% is absent. So that part is actually coming from the hot part or the warm hot part. So we call it warm hot intergalactic medium or WIMPs. So they are too hot. I mean the range of temperature is from 100,000 to 10 million Kelvin. That's why we call it warm and hot. And from this because it is too hot, that the hydrogen atom or the gases there will be in the ionized condition, so they will not be forming neutral atom, they will be in ionized condition. So we cannot use the same trick, the trick we have used in alpha forest. So so finding the beam has been a real challenge. So how to find this thing? So people have used different, so you can find beams, then you will have to be using this x-ray light or some ultraviolet light. So people have used these things, but there are some uncertainties involved in this procedure. So instead of this thing, people use another thing which I will describe you, and which is the so for in order to understand how did they detect this beam, so let's consider the situation. So you have Earth. If you have some kind of signal here, let's say lightning is happening on this region, So this lightning, I mean the formation get actually transformed in this ionosphere. This is the ionosphere. So this light goes and passes and reflected back or some to other part of the earth. So if you see you have white light, it has different colors. So if it passes in a region where there are no free electrons, so it will be moving fast. And if there are free electrons, so it will be losing energy by interacting with these electrons. So it will slow down. One thing, and second thing, I mean these electrons, I mean this stuff, this is actually a kind of dispersive medium, so it will respond to different color of light differently. I mean this the low frequency component will be slowed down more as compared to high frequency component. So you can see that effect in this picture. The red one is lagging behind and this one is going. So there are these two effects. So this dispersive, so by calculating the dispersion of this information, you have a pulse here, I mean just lightning, and you should, that impulse, I mean I mean dispersed, I mean the signal is bit distorted, and we measure that dispersion, and after measuring that dispersion you can estimate the number of electron or the stuff in its way. So all we need now from this example, uh, we will be using this physics and to detect the rest of the baryonic matter which we know, I mean, is hiding in the WIMP. So all we need is a bright flash of radio waves somewhere in the distant universe. Recently, a naturally occurring phenomena allows us to find all the missing WIMP. So what's that? So in 2007, astronomers found the first fast radio uh, bursts. So what are these things? It is a very this produces this fast radio burst actually produces a very short duration pulse of intense radio waves. So you can see this frequency and time. So here this amplitude. And now, I mean, the astronomers have found many fast radio bursts. So you can see this is the all sky map, and you can find these flashes of fast radio bursts very often coming from various parts of the universe. So there is a question, I mean, what kind of things are producing these fast radio bursts? So there are many theories. So there are many theories then published events. It could be exploding stars, colliding neutron stars, colliding black holes, comets, asteroids, evaporating black holes. So there are many theories. I mean, still we don't know, we are not that much sure, but it could be neutron star, or it could be magnetars. Magnetars are actually the magnetic stars which are highly magnetic remnants of massive dead star. Astronomer had long suspected these objects could be source of fast radio bursts. So they were thinking that this could be the source of fast radio bursts. So, but I mean, however, there's only a handful of magnetars known in our Milky Galaxy. But recently they found one in this experiment, which is Shime telescope in Canada was first to report it had detected a fast radio burst from a magnetar near the Milky Way center. So using these, so for our purpose, it doesn't matter where these fast radio bursts are coming from, and we can make these predictions about the missing baryonic stuff. So this was the paper which was received in 2019 and published in May 2020 in Nature. A census of baryons in the universe from the localized fast radio burst. So they say the sense of nearby. So they also describe, I mean, people have used different techniques to to see this thing. It's not that they are these guys are the only one who did this thing. So people were using different techniques to observe the invisible baryons, absorption line spectroscopy, but they say there are large uncertainty, and the quasar spectroscopy and things like that, and also this Zardovich analysis and things like that. So they say here we report a measurement of baryon content of the universe using the dispersion of a sample of localized fast radio bursts, and this technique determines the electron column density along each line of sight and accounts for every ionized baryons. So this is important. We augment the sample or next they have used these redshifts, the complete sample, and here is their number, I mean the baryonic density. This is actually the density of baryons divided by critical value. This omega parameter is actually density of baryons divided by critical value is 0.01%, and this independent measurement is consistent with values derived from the cosmic microwave background and from Big Bang nucleosynthesis. As I described in early slides, we know that it should be there. Now they have seen it, that these missing baryons are hiding in this WIMP, the warm and hot intergalactic medium. So now they have found the 50%, rest of the 50%. So it was, I mean, this experiment, you can see it was like examining the beam of a far away lighthouse in order to study the fog around it. So you have flashes, not that quite often, and you have a very foggy medium between the lighthouse and you, and then you detect what kind of this fog is about. I mean, so they validate the claim that BIM makes up rest 50% of the baryonic matter. Here they have this plot which shows the dispersion measure of the cosmic, or on the horizontal axis they have the redshift of fast radio burst. So you see a linear relation, and yeah, so these are these different measurements. Okay, so finally we now know the rest of the 50% of baryonic, missing baryonic matter. This is this one, warm and hard, and the cosmic budget of ordinary or baryonic matter is now complete as estimated, as predicted by the cosmic microwave background radiation and Big Bang nucleosynthesis. So we are done here. So I think last slide, yeah. So now another very difficult challenge is waiting for us. Just for, I mean, fun, I mean, I've included this slide. So in case of missing baryon, I mean, you know, I mean, from the theory of very early universe, that this missing baryon should be there, and then you kind of saw it. I mean, and in this case the visibility of crescent moon, I mean, uh, so according to science, I mean, today the astronomy can accurately establish the time of birth of the new moon with the accuracy of second and its likelihood of being visible. So in this case, I mean, if science says that let's say that moon is not visible, and you and someone sees it, I mean, so to me, I mean, it looks like opposite to the case which I have described earlier. I mean, so theory and science, you cannot have it. ठीक है, साइंस कहती है कि भाई यहाँ पे आज आप चांद जो है वो नहीं देख सकोगे, विजिबिलिटी इतनी नहीं है, और फिर हमारे जो डिटेक्टर्स हैं वो जो है उसको देख लेते हैं. तो यहाँ पे जो एक अच्छा खासा चैलेंज है कि इसको जो है, इस कंट्रोवर्सी को भी देखा जाए कि किस तरीके से ये चीज़ जो है पॉसिबल है. हाँ, ये हो सकता है कि साइंस की कहा जाए कि आज जो है आप जो है नेसेंट या न्यू मून जो है उसको आप देख सकते हो, और फिर किसी को वो नेकेड आई से नज़र नहीं आता. नेकेड आई से नज़र नहीं आता, उसमें ये है कि मौसम ऐसा है, वो चीज़ जो है वो तो थोड़ी समझ में आती है, लेकिन ये चीज़ जो है समझ में नहीं आती. खैर, ये मैं जस्ट फॉर जो है फन ये चीज़ डाल दी थी. तो यही मेरी लास्ट स्लाइड है. आई विल स्टॉप हियर एंड यू गाइस कैन हैव क्वेश्चंस.